a new topic which you have never learned before, but you definitely experience electrostatics. Okay, so we experience electrostatics every day. However, there are some very small things when you go and break into the molecule or the particles. Okay, so this is what we want to study about electrostatics today, right? So look at the learning outcomes. Electrostatics is being concluded by Coulomb. So Coulomb is the one who discovered electrostatics. So basically Coulomb's law determines about the electric force. Okay, so this is electric force on the systems. Okay, and as a normal symbol for force is always being given by symbol F, so including electric force also. Okay, so if we have electric force, definitely it is caused by electric field given by symbol E. Okay, so how do they both related? Force and field, how are they related? Right, and electric field for different types of arrangement. For point charge, this is for point charge. Electric field for conductor. Electric field in between two parallel plates, right? And further on, another terms which is electric potential energy, so given by U. So this is just like a potential energy, okay? But now it's related with electrostatics. Followed by electric potential, another terms. And if we have energy, we have work done also. So basically there are four main terms in this topic: electric force, electric field, electric potential energy, and potential. Okay, so we will look at them one by one. And finally is potential. Okay, so I guess most of you played this in your primary school, right? So when you draw a plastic ruler near to the paper, the small pieces of paper, okay, the green color, this is your paper. Yeah? Okay, so if you draw a plastic ruler without doing anything, nothing will happen, right? So when you want to show magic to your friends, you will secretly rub your plastic ruler with a cloth. So after you rub the ruler and you draw the ruler near to the paper, what will happen? The paper will stick on the ruler, and you will tell your friend this is magic. Okay, but in fact, I guess most of you know already, right? It's not because of magic, but because of electrostatics. So what happened here is when you rub your ruler with cloth, the charges, okay, the positive charges will be, okay, so let's say this is your cloth. So the positive charges will somehow be, we say it's being taken and jump to the cloth. So what happened is left only the negative or majority of negative charges on your plastic ruler. So when you draw your ruler near to the paper, so this paper, when they are in neutral, right, they have both the positive and negative charge. So when you draw the ruler near to them, what happens is, okay, the positive charge will be attracted by the negative charge in your ruler. So because of this electric force, then the paper will stick to the ruler. Okay, so another phenomenon that you always encounter is when you are in the aircon room, and especially when you are wearing let's say a plastic slipper. So if you are in the aircon room for too long, and especially when your skin is dry, so the moment when you touch the doorknob, you feel the electric force. There is a spark in between your skin and the doorknob. Okay, so that is also because of electrostatics. So due to the friction between your plastic slippers and the floor, okay, there are some charge is being lost through the plastic slipper. So you are a charged body now. So when you touch the doorknob, the electrostatics, due to the electrostatics, so there will be a charge jumping from the doorknob to your hand, right? So you feel the electric force. Okay, so now let's learn the theory part, which is quite boring. Okay, these are the phenomena that we always experience, but what happens is when we have to look into the small particle, and especially about the theory parts. So the things that you always experience, the sparks, the things that you can see, is what we call as electric force. Okay, electric force is given by symbol F, and as usual given by the unit of Newton. So what does Coulomb's law mention? Okay, so I mentioned when both of the charges having the same sign, they will experience repulsive force. So same charges repel, opposite charges attracts. So this is just like our norm where opposite sex attracts, same sex repel. Okay, that is for the normal norm. Yeah, all right. So Coulomb's deduced that the electric force is directly proportional to the products of two charges, directly proportional to the products of two charges. So let's say if charge 1 having 10 coulomb and charge 2 having 20 coulomb. So how strong is the attraction or the repulsion depending on the charge inside them, okay, compared to another one, 1 coulomb and 2 coulomb. So this one will definitely has higher electric force as compared to this one. Okay, and electric force is also inversely proportional to the square of the distance between the two charges. Okay, so it's also inversely proportional to the square. So if the distance R1 and R2, okay, so if R2 is smaller than R1, if R2 is smaller than R1, then the force will be higher also. So force 2 will be higher. Okay, so if you combine these two together, we can conclude that electric force is directly proportional to the charge and inversely proportional to the distance. So if you want to put them into a formula, if you still remember, yeah, so it's equals to Q1 times Q2 divided by R squared. So if you want to convert the directly proportional sign to the equal sign, you have to add a constant in front. Okay, so this is the formula for our electric force. Okay, so the formula for electric force. So electric force is a vector. What do you understand by vector? When we mention what vector means, it will have both the
magnitude and direction.
Yes, magnitude and direction. So if it is a vector question, which means positive or negative, it doesn't matter. Okay, positive or negative will not affect the value of your will not affect your magnitude. Okay, it doesn't mean that -5 is smaller than +5. No, it's the same strength. What is the difference is the direction only, right? So same goes with your electric force. Since it is a vector, which means we have to always look at the direction first before you move on to your magnitude. So how do we determine the direction? Remember just now when we mentioned about same charges repel and unlike charges attract. Okay, so let's say if we are having two charges here, Q1 and Q2. Q1 and Q2 here, yeah? Okay, so since both of them, they are having the same charges. So if you are asked to determine what is the electric force experienced by Q1, okay, electric force experienced by Q1. So this is your study subject, right? So what will be the force acting on Q1? Since Q2 is also having the same charge as Q1, so the direction of the force experienced by Q1 will be moving to the left. So that will be your electric force. So this electric force will be calculated by Q1, Q2 over R squared. So Q is always the symbol for charge. Okay, Q is always used as the symbol for charge in the unit of coulombs. So short form C. And R is the distance between your Q1 and Q2. So in the unit of meter, SI unit. And K, the constant, is Coulomb constant given by 1 over 4 pi epsilon naught. So this epsilon naught is permittivity of free space. It's also another constant. Okay, so you are allowed just to directly use this value, 9 times 10 to the power of 9. So bear in mind, your Coulomb constant, the unit of your Coulomb constant, they are all in SI unit. So since a Coulomb constant is being used in this equation, so all the value that you plug in for your Q and your R must be SI unit also. Okay, so I repeat, yeah. Since the unit for your Coulomb constant is SI unit, which means whatever value that you plug in for your Q and also for your R, all these unit must be in SI unit. Okay, I have marked your midterm, some of your midterm, and I discovered there are few of you didn't convert some of the value into SI unit. Okay, it makes very much different. Okay, so what is the difference? Just imagine ringgit Malaysia and USD are a lot of different. 1 USD and 1 ringgit Malaysia, it's a lot of difference. So if you think SI unit is not important, then you might have to pay the difference in USD for me. Alright? Okay, so as an engineer, please take notes on the unit, Alright? So if we are having a different charge, let's say Q3 and Q1 here. So instead of having a positive charge here, now it is being replaced with a negative charge. So the force experienced by Q1 here now will be going to the right. Okay? So this is just like you are drawing your free body diagram, remember? So instead of the all forces that you have learned about the weight of the object, the normal force, the friction force, and the one that you learned in the previous topic, which is the buoyant force, now we introduce another one, which is electric force only. Okay, so electric force exists when there is charged particles, or when there are charged particles. Alright, so let's move on in solving a calculation regarding electric force. So the steps that I have given here is, if you see the word force relates to vector. So if this is a vector, then always think about the direction. Then only move on with calculation. So once you have show your direction, okay, let's say you have two directions here, so F1 and F2. Then only move on to find what is the value of F1 and what is the value of F2. Then you combine your net force. So for this one, since they are not in the same axis, then you have to use Pythagoras theorem to find where is the net force. Okay, both the direction and the magnitude. Right? So let's solve this work example together. What is the electric force on a positive charge which is positioned at point O? So which means if I put a positive charge here, what will be the electric force experienced by this positive charge? So let's follow the steps. Step 1, determine the direction. So draw your free body diagram. First, look at Q1 first. The direction of the force experienced by 2 nanocoulomb will be going to the right. Okay, because of same charges. So F1 is equals to the direction of the force apply on your positive 2 nanocoulomb due to your Q1. How about F2? So F2, if we look at the relationship between these two charges, so it will be going towards your negative charge. Okay, so these are the two directions that you have identified. Okay, or if you want to make it easier to identify, then F1 will be equals to force in between point 1 and point O. So we put 1 O, and F2 is the force in between point 2 and point O. Okay, so secondly, once you have already determined the direction, now let's determine the magnitude. Formula for electric force, okay, Q1 Q2 over R squared. So find the force in between 1 and O. So rewrite your equation. So it will be in between Q1 QO divided by the distance in between 1 and O squared. So write down the value. Q1, which is 6 nanocoulomb. So nano is times 10 to the power of negative 9. QO, so divide by the distance between them, which is 4 centimeter, convert to SI unit and square. So you get 6.75 times 10 to the power of negative 5 nano. Okay, so move on to find the force in between 2 and O. So rewrite the equation, becomes kq2 cube O divided by the distance squared. Q2 is -8. So remember, a vector question, we do not plug in the positive or negative sign. So just put 8 times to the power of -9. No negative sign in front, because positive and negative is determined by the direction. So what is the distance between them? This is a right angle triangle. So the distance is 5 centimeter. And we get 5.76 times 10 to the power of negative Newton. Okay, so this is our step 2. Move on to step 3. Find the net force. Okay, so if you look at the direction, just now our F10 moving to the right, F20 moving diagonally downwards. So these two, they are not falling on the same axis. So if they are not falling on the same axis, we have to do somehow the resolving, right? To map them into x-axis and y-axis, remember? To find what is the x component, what is the y component. Okay, so what you have learned in your first semester in your free body diagram, the total force in your x-axis. So let's assume going to the right, positive. So it will be equals to F10 plus your F20 has to be resolved to x and y axis, right? So it will be F20 x-axis and F20 y-axis. So since it is moving in the opposite direction, so this one will be in negative value. Okay, so I will draw the whole picture here. This is 4 centimeter, 3 centimeters, it will be 5 centimeter, and our force okay, so what is the value of this? To resolve this one to your x-axis, assign theta here. Okay, so this one will be your F20 cos theta, right? So I presume most of you know how to do the resolving. Okay, so if I want to resolve to my axis, it will be the hypotenuse cos the angle, and it goes to the x-axis. Okay, so F10 is 5.75 times 10 to the power of negative 5 minus F2O 5.76 times 10 to the power of negative 5 cos theta. What is the value of cos theta? Internet connection very poor. Is it, how about now? Is it better? Okay. So let's move on, Continue. Okay, so 5.76 times 10 to the power of negative 5. Previous slide, this one. Okay, cos theta. So you can choose to find the angle of theta, or if you have a complete dimension of the right angle triangle, cos theta is also equals to 4 over 5, right? From the diagram here. So replace the whole cos theta with 4 over 5 only. So you get a total of 2.14 times 10 to the power of negative 5. So since this is positive value, so it means the direction is going to the right. And now move on to find our Fy. So if you want to assign going down as positive, so Fy only equals to F2O in y dimension. So F2O in y dimension here, or you can say it's actually equivalent to here, right? So resolving your F2O to y dimension, it will be the hypotenuse sine theta. Okay, so if you have already known how to resolve to the x dimension, which is in cos, then y will be in sine, provided the angle is the same. So F2O 6.75 times 10 to the power of 5.76. Sine theta is equals to 3 over 5. So 3.46 times 10 to the power of negative 5. So positive value, it will be going downwards. So in order to find your net force now, So it's your fx squared plus your fy squared and root square again. (4.06 times 10 to the power of -5 Newton. Okay, so if you want to draw them into a diagram, which means it will be 2.14 times 10 to the power of -5 to the right, and 3.46 times 10 to the power of -5 going down. So your direction of net force will be somewhere here. Okay, so if you would like to find the angle, so you can find it through tangent. So your Fy over Fx. Okay, so basically you just have to know how to find the net force, right? So any more question about electric force?
Would you get clear? No.
No, huh? So let's move on to electric field. Okay, so electric field is given by symbol E, and the unit is Newton per Coulomb. Okay, Newton is the in force over charge. So electric field is actually a region around a charged particle. Okay, so if you have a charged particle here, so surrounding the charged particle, there is electric field. So I usually call electric field as the aura of the charge. Just like if you are a very handsome and very pretty person, so you are releasing your aura to the surrounding. So electric field is just like the aura of the charge. Okay, so as long as something is charged, then there will be aura, there will be electric field around the charge. Okay, so this electric field can be felt by another test charge. There will be aura. So if you put another charge near to the field, then this charge will experience an electric force. Okay, so electric force is related with electric field by this one. As long as, okay, for example, okay, let's say if this is a very pretty girl, okay, this is a very pretty girl here, okay, I don't know how to draw. All right, so you will be having your aura surrounding you. So people, when they go near you, they will be attracted, right? So let's say if there is another guy here, okay, so when this guy go near you, like it's present in the area where you are releasing your aura, so this guy will be attracted, whereby his eye will be looking at you whenever you go. So this is what we mean by electric force, the action taken by this one, which is turning his eye on you whenever you go. Okay, so electric field is the aura without any action first. All right, electric force is the action, is something that you can see and something that you can feel. All right, so the force, the amount of force that will be experienced by this one is depending on how strong is the aura, right? If you are releasing a very strong signal, come and talk to me. So if the field is very strong, then the force will be very strong too, right? So the force that felt by the force that felt by the test charge divided by the magnitude of the test charge. Okay, so which means the electric field is depending on the force in between these two divided by the charge of this one. Okay, because we want to study what is the aura released by this charge, right? And the characteristics of electric field, so I put 3 stars here, which means this is super important. Electric field always point out from positive charge and point in to negative charge. Okay, so it means if it is a positive charge, then your electric field is always moving outwards. If it is a negative charge, then your electric field is always moving inwards. Okay, so let's look at the diagram. Okay, electric field is also a vector. Okay, so how do we determine the direction? Based on the principle just now. If it is a positive charge, then it will going upwards. So let's say this is a positive charge here. And if you are asked to find what is the electric field at this point, so going upwards, so it will be going to this direction. So that is the electric field. Okay, so to find the value of electric field is given by kq over r squared. You just eliminate another q because there is no interaction yet. So the electric field created or electric field generated by this q1 is equals to k times q1, the value of q1 divided by the distance. Okay, the distance between your charge and the point that you would like to study. Okay, so if it is a negative charge, the direction of the field experienced by this point P will be going inwards, which is this direction. Okay, again, K is Coulomb constant and in SI unit. So Q is in Coulomb, R is in meter. Okay, so same with electric force. The steps in order to solve the electric field is also come first with the direction, followed by magnitude, and then the field. Alright, so it's also similar like you are drawing your free body diagram, but now you have to draw it in terms of electric field. Okay, so now let's solve this work example. So now we do not have anything here in point O. Okay, so you are asked to find what is the electric field at this point. So first thing first, determine the direction. So electric field generated by Q1, which is E1, will be moving away from Q1, right? Because positive charge is always moving outwards. How about E2? Going inward for negative charge. So your E2 will be going towards your Q2. So once you have done with your direction, let's move on to find the magnitude. So E1 is equals to KQ1 over R1 squared. So the distance in between your charge and the point that you would like to study is your R1. So 9 Coulomb constant. Q1, 6 times 10 to the power of negative 9 distance, convert to SI unit. 33.75 times 10 to the power of 3. E2, so this is about Q2. Q2, negative 8 nano. So again, no negative sign has to be included because negative is determined based on the direction. So we have already calculated the distance in between point O and Q2 is 5 centimeters. Okay. So we have done with magnitude, and now we would like to find what is the net field. Okay, so draw the diagram again. Okay, E1 is here, E2 is here. So same as just now, since they are not on the same axis, we need to do resolving. So total field in x direction is equals to, let's assume going to the right as positive. So it's equals to E1 plus negative E2. If this is your theta, then E2 cos theta. E1 33.75 times 10 to the power of 3 minus E2 cos theta is 4/5. So positive value means it is going to the right. And now move on to find your field in y direction. So let's assume going down as positive. So it will be E2 sine theta. So sine theta is 3/5. And you get 17.28 times 10 to the power of 3. Positive value means it is going downwards. So if you would like to draw them into your diagram, you get EX and EY so your net field will be somewhere here also. So how to find the net field? Use Pythagoras theorem. Unit Newton per Coulomb. Subsequently, find the electric force experienced by a positive charge 2 nanocoulomb position at O. So now I move a charge to here. What is the electric force? So you can use the long method just now to find your electric force, or there is another shortcut. If you still remember one of the definitions just now, this one, electric field is equals to force over charge. So we can say that force is also equals to charge times electric field. Alright, so this one, it means the electric force experienced by the charge, let's say this one, charge 1, is equals to the charge in your Q1 times the electric field experienced by Q1. Okay, I repeat that. The electric force experienced by this Q1 is equals to the charge in this Q1 times the electric field experienced by this one. Just like the phenomenon just now, the analogy just now. Alright? The electric force, the action taken by this boy, I use another card. Okay, the action taken by this boy is depending on the charge, or we say the current, inside the boy, and also the signal received by this boy. Okay, if I'm a very brave person, okay, so if let's say if this boy is a very brave person, alright, and he is also receiving a very strong signal, the electric field, very strong signal, so the force, the action that taken by this one will be very large also. Alright, so let's double check our answer with this shortcut method. Force equals to the force experienced by 2 nanocoulomb is equals to charge in the 2 nanocoulombs times the electric field experienced by this 2 nanocoulomb, which is actually equals to electric field at point O. So 2 nanocoulombs times the net field just now, which is equals to 20.3 times 10 to the power of 3. And you get 4.06 times 10 to the power of -5. Isn't it the same as the work example 1 that you have calculated by using the long method? So it's in fact the same answer as your F when you are using this method, right? Okay, so we shall move on to see the electric field pattern. So electric field is always going out from positive charge, like this. And if let's say you have a neighboring negative charge here, then this positive direction of electric field will go all the way into your negative field. But remember, yeah, it must be radially. When we mention about radially outwards, for positive charge and radially inwards for negative charge. So it means actually it is actually coming out straight from the center of the point charge, or we can say your electric field must be 90 degrees relative to the surface. Okay, so when it goes into your negative charge here, if you look at here, they are all 90 degrees relative to the surface. And if you have two neighboring positive charge, what will happen is there will be a vacuum here in which electric field is equal to 0, because your positive charge, the electric field is always going outwards. You can't expect them to go here and stop somewhere. Okay, so it will be a vacuum at the center. So let's say if you have a parallel plate which is negatively charged, so the electric field will just go in like this, whereby the direction of the field again is perpendicular to the surface, right? So you can predict the pattern of the electric field based on the different shapes of the different shapes of your charge. So now move on to the electric field in a conductor. So a point charge is just a particle, right? So a conductor, it will be something bigger with a lot of particle inside. So if this is a neutral conductor, it doesn't mean that it doesn't have any charge. A neutral conductor doesn't mean no charge. A neutral conductor means your positive charge, the amount of positive charge is equal to the amount of negative charge. Okay? So if now the conductor is positively charged, so if it is positively charged, it can either be all the negative charge has been discharged, okay, so left only positive charge, or you have a very minimum amount of negative charge. So let's assume left only positive charge inside the conductor. So what happens is the charges inside the conductor will rearrange due to Coulomb's law. Okay, so your positive charge will separate it as far as possible, just like this one. Okay, so what happens is there will be a region with zero magnetic field right at the center. So that's why the electric field inside a conductor is always 0. Okay, however, on the surface here, they will be positively charged. So if you look at the diagram here, this one, the surface of the conductor will be positively charged, whereas at the center here, you won't get any electric field because all the positive charge has been separated as far as possible, so there won't be any charge at the center. And because they are all positive charge, so at the center region, there won't be any electric field. Alright? So your electric field inside the conductor is always 0. And outside the conductor, the electric field is perpendicular to the surface of the conductor. Okay, and all the charge will be on the surface only. So that is the characteristics of electric field in the conductor. So if you look at here, the electric field in the conductor, hold on. Okay, so when we have an empty electric field at the center, this is what we call as Faraday's cage. So Faraday's cage, what happened here is there will be a electricity conducting outside the conductor, but whatever things that stay inside here will be safe. So this one, you always encounter it when you are inside the lift, if you are talking on the phone, right? So when you go inside the lift, immediately there won't be any signal. Why? Because the lift is a big conductor. So when you go inside the lift, you are actually protected by this conductor, so there won't be any signal received. Another phenomenon will be your house. Okay, your house. Okay, so someone that stay inside here, even though the lightning strike on the house, okay, it will be only outside, right? So someone inside, it will be safe also. Or let's say if you are driving on a heavy storm, okay, so again, human that sit inside the car will be safe even though the car is being struck by the lightning, okay, because of the Faraday's cage. So someone that stay inside will be safe and sound, okay. But but eventually, okay, however, the accident will happen, okay, due to the very large amount of the electricity, or we could say current. What happened is the car might be burned, okay. So the person who sits inside the car, it won't die because he won't die because of the charge, but he dies because of the fire, right? So this is what we means by Faraday cage here. So due to the zero electric field inside the conductor, so the subject inside the conductor, it won't be affected by any effect of electrostatics. However, there are other factors, let's say the fire or the usually it's the fire, but they won't be affected because of the electrostatics only, right? So that is the electric field in conductor. And electric field in between two parallel plates. So if you have two parallel plates just like this, the electric field in between will be uniform, which means in the whole area here, the electric field will be just equals to V stands for potential difference, which is in voltage, and D is the distance in between the two plates, so it will be the same, okay. So which means the electric field here at this point and at this point, at any point in between the two plates, they are the same, okay. E1, E2, E3, E4, E5, okay. So that's all for electric field and electric force, okay. Let's have a break of 5 of 7 minutes. So we come back at 11:10. So I give you some time to digest both electric field and electric force. Okay, there is a question about Faraday's cage. So if it is Faraday's cage, then inside the cage, inside there is no charge at all. But it's only on the surface, yes. Then the charge is the same. Yeah, the surface, it will be the same because it's the whole individual that is being charged. Okay, so on the surface, let's say if it is charged up to 3 coulomb, then on any part of the surface that it will be 3 coulombs. Okay, so everyone's here. I would like to show you something which I guess you have seen this before or never, but something that is what we again call as magic. It's not magic lah, huh? Okay, so this is a plasma ball. Can you see this one? This is a plasma ball, yeah? So if we zoom in, you can see in the center, this one look like a tower, right? So this is actually a Tesla coil. Okay, the function of Tesla coil is to step up the voltage to a very high voltage. So inside here, the voltage is up to 1000 volts. Okay, so when I turn on, this is what happened. We always see this when someone go to look for the witch and they will go and predict something, ask the ball something about the future or about something. Yeah. So if you look at here, okay, at the center here, the current or the voltage is being stepped up to a very sorry. Okay. It is being stepped up to a very high voltage. So this is a very highly charged point at the center. So what happened is, surrounding by this glass ball, inside the glass ball is all the inert gas, or we say the neon gas. Okay, the gas that fall in the group 8 of your chemistry table. Huh? The what table? I forgot already. Okay, so because of the high electric field inside, okay, remember just now I mentioned, yeah, when you have something which is very highly charged, let's say at the center point, okay, surrounding it will be full of electric field. And this electric field is something that can give the power, okay, give power to the electric force. All right. So what happened is, because of this one, so the particle of the inert gas, they are being excited. So they tends to move. So that's why it will be illustrated by the color lines. Okay, so if you want to further see how does this help here, okay, this is a fluorescent light, the fluorescent light tube. Okay, I do not connect it to any power supply. Okay, but what happened is, when I draw near my fluorescent tube to the plasma ball, you see what is happening. Okay, the fluorescent tube actually light up. So if I move my hand to the center, okay, only the part where it is near to the plasma ball to where I hold the tube is being light up, but the part which is behind is not lighted up. Okay, so what happened here is, again, okay, because of the electric field here, so the particle inside the fluorescent tube is also being excited. So the charge is being ionized in your tube. So that's why the light will light up. But why is it only to the place where I hold the tube? Okay, so this one is because of the grounding. Yes? This is kind of a trick that we can use for
It is
magic.
because your hand has electron, right?
Sorry, can you repeat? I turn on my volume first. Yeah. Again, what is your question?
So because it is your hand has electron, right?
This is because of the grounding. Grounding is because I'm actually standing on the ground, and we human is actually a good conductor, a good electricity conductor. Why? Because we are formed, nearly 70% of our body is formed by water. Water is a good conductor. So that's why we can conduct electricity. So from place where I hold my hand, okay, this is where the current, so-called the current, coming from that plasma ball to the end here, to my hand, and from my hand go to my feet and go to the ground. So this is the grounding. If you go into electrical engineering, or if you have someone who is in the field of electricity, you will always hear about the word grounding. Okay, so if next time if you would like to try out this one, you can come to my office and you can try the magic. Yeah, okay, but for this round I only demonstrate to you. Okay, this is something quite interesting, so let me tell you what happened in between. Okay, oh, there is a work example, right? So okay, just now this is the plasma ball, right? At the center, this is a Tesla coil. So right at the center here, the voltage, it could be up to 5 kilovolts. Okay, so when you have a very high voltage, means the charge inside is also very high, which means the Q is very high also, right? So what happens is when your Q is very high, surrounding here, there is electric field. So because of this high electric field, the gas particle get excited. So this gas particle is actually inside here. There are no, like what we said, the oxygen, the nitrogen. These are all the inert gas. So inert gas, they have their own colors. So when they get excited, okay, they are showing their color like what you have seen just now. So if you remember just now when I touch my finger here, yeah, this is my finger. Okay, when I touch my finger, what happened here is, because I'm creating a grounding system, this is to the ground. Okay, so instead of now the charge is being randomly discharged through the inert gas inside the glass ball. Now most of them, they would prefer to go through my hands and go down to the ground. Okay, that is the characteristics or the nature of electricity. They will prefer to go to the ground, whereby it actually created a bigger potential difference. So we will look at potential later, yeah? Okay, so what I want to tell you here is, this is a plasma ball is where we can, just now when I mentioned about we cannot see electric field, right? We can only see electric force, but a plasma ball is something that you can see how does electric field work, and at the same time it also shows you about the electric potential, which we are going to discuss later. All right, so I guess we will come back to this work example later, but move on to potential first. Okay, so potential and potential energy. So potential energy is a kind of potential energy. Electric potential energy is the potential energy that exists due to the electrostatics. Okay, so energy is given by a symbol U and is in the unit of joule. So there are two types of potential energy. One is potential energy of the charge, okay, a point charge, and the potential energy of the whole system. So a good news here is potential energy is a scalar quantity, so you don't have to care about the direction anymore. Yeah, you don't have to draw the line, you don't have to do the resolving, you don't have to do the Pythagoras theorem, you don't have to learn about trigonometry. Okay, so if you see the question is about potential energy, then you have to thank me. Okay, so it's a scalar question, so it means you don't have to look at the direction, but instead now you have to include the positive and negative sign. Okay, so the formula for potential energy is given by K Q1 Q2 over R. This one. So your distance now is not the square of the distance, but only distance. So Q1 is the charge in Q1, Q2 will be the charge in Q2. But the difference is you have to, if it is a negative charge, then you have to include the negative charge. Right? So that's why if you look at the formula that we give you here, okay, for scalar quantity, we write the Q in terms of capital letter. So capital means you have to include everything, including the sign. Just now, if it is electric force, right? Remember, it will only be K, but small capital Q1, Q2 over R squared. So this small capital means you only include partially. Without the sign, right? So even the formula itself has already hinted you whether it is scalar or vector. So let's try out this work example. Find the electric potential energy when a 2 nanocoulomb charge is being placed here. So this is a scalar question, so straight away just look at the magnitude. So the energy owned by this charge is the product of the energy between charge 1 and point O plus the energy in between charge 2 and point O. So plug in the value K Q1 QO divided by distance 1O plus K Q2 QO divided by distance between charge 2 and charge O. So 9 times 10 to the power of 9. Q1 6 nanocoulomb. Charge at point O is 2 nanocoulomb. Divide by the distance, 0.04. SI unit, Q2 is negative nanocoulomb. QO is positive 2 nanocoulomb. The distance, 0.05. So, can you find the value of the potential energy of the point at O? So you get a value of negative 1.8 times 10 to the power of negative 7 joule. So negative, if you get a negative value, it means based on the sign convention. This one, it means the work is done by the electric field. Okay, which means the charge, this 2 nanocoulomb, does not need to work hard in order to stay here. The electric field itself is welcoming the charge to stay here. Okay, so what is the electric potential energy of the system? So if it is system, means we will have to look at all types of relationship. So it will be the energy in between 1 and O, energy in between 2 and O, energy in between 1 and 2 also. So whatever kinds of, every possible kinds of combination have to be included if it is the energy of the whole system. So this 2 you have already found, which is 1.8 times 10 to the power of negative 7. So the system is 14.58 times 10 to the power of negative 5 joule. Okay, again, negative here means the whole arrangement is being welcomed by the field. The field itself, it's allowing all the charge to stay in this position, right? So look at electric potential now. So electric potential is given in the unit of volts. So same as electric field just now, if you have a charged particle, surrounding it will be the aura, right? Electric field. So this aura consists of both electric field and also electric potential. Okay, so if you remember the plasma ball just now, I back to the slides of the plasma ball. Okay, so this plasma ball just now I mentioned about at the center here, this is 5 kilovolts at the center. So surrounding it, there will be electric potential. So let's say it will, this is 5 here, so when it comes to outside, let's say it will reduce to here, let's say okay, here let's say it becomes 4 kilovolts, and here 3 kilovolts, and here let's say it's 1 kilovolt, right? So there will be electric potential surrounding a charged particle also. So let's say when it comes to my hand, for example, yeah, it has reached 1 kilovolts. Okay, so what happened is, between my hand and where I stand, this is 0 volts. So there will be a potential difference in between my finger here to my feet. So due to this potential difference, which is 1 kilovolts, so the current would prefer to go through my body and down to the ground. Okay, but in fact that won't be that much, okay, because the potential difference tends to decrease when the distance is further. Okay, so potential difference is related with the energy, just like how electric field is related with electric force. Electric potential is related with energy, and energy is the ability to do work, right? So another terms you have to know here is potential difference. Potential difference is the difference in potential whereby it relates with the position. Okay, so it will be the final potential minus the initial potential. And equipotential means, means same. So same potential, which means on equipotential surface, the potential are the same. Okay, so means if you have an equipotential line, it means on the line itself, all the point, the potential is the same. And a very important characteristics here, equipotential line must be perpendicular to the electric field lines. Equipotential line must be perpendicular to electric field lines. Okay. So what is equipotential lines? Okay, the one in round is your equipotential line. So equipotential line is always follow the shape of the particle or conductor. So if this is your charged particle, which is round, then your equipotential line will be mimicking the shape of your particle, which is also in a round shape. So that's why, if you remember, your electric field is perpendicular to the shape of the particle or the conductor. So likewise, it will be perpendicular to your equipotential line. So in order to determine your electric potential, it is given by KQ over R only. And good news also, it is a scalar, so you don't have to look at the direction, but instead you must include the positive and negative sign. Okay, so whether it is for positive or negative, the calculation is the same. It's just that take notes on your charge. So let's solve this question. Work example 5 together. Find the electric potential at point O. Okay, potential at point O. So it will be equals to the potential, the electric potential caused by Q1 plus the electric potential caused by Q2. If I stand here, I can feel the potential of both Q1 and Q2. So B1 equals to KQ1 over R1, oh no square, sorry, over R1 plus KQ2 over R2. So plug in the value. Q1 6 nano, that will be your R1, which is 4 centimeter. Q2 negative 8 nanocoulomb divided by the distance, which is 5 centimeter. So we get 90 volts. So which means here, at this point here, the negative potential has higher influence. If you look at the distance and also the charge value, it makes sense, yeah? Your negative charge has higher charge, which is 8 nano. Positive charge only 6. So if you stand here, it means definitely the negative charge will have higher influence on the point as compared to the positive charge. Subsequently, part B, find the work done to move 2 nanocoulomb charge from infinity to point O. So work done is equals to the charge times change in potential. So work done by the 2 nanocoulomb charge, right? Times the change in potential, the final position minus the initial position. So that final position is at position O, initial position is infinity. So 2 nanocoulomb, 2 times 10 to the power of 9. The final potential, point O, negative 90. So scalar, just plug in the sign together with the value, minus potential at infinity will be 0. How do we know? KQ over R. When your R is infinity, in your max, anything divided by infinity will be equals to 0. So you get negative 1.8 times 10 to the power of negative 7 joule. Okay, so it means the charge doesn't have to work hard in order to, this one negative means the work done by field. So it means the positive 2 nanocoulomb charge doesn't have to work hard in order to climb to here, but the electric field itself will welcome the charge to go here. How do we know? Because at this point, remember your potential is negative 90 volts. So negative seems to be attractive to the positive charge in order to reach here. Alright, so the charge doesn't have to work hard. So if you get a negative work done, it means the work is done by the field. Okay? So electron volts, this is a term just for electricity. Okay, electron volts is a measurement of energy, just like joule is a measurement of energy. But instead of we put everything into joule, okay, for a smaller value, we will use electron volts, and especially when it is used to mention or to describe the energy owned by the charges. Okay, so 1 electron volts is equals to 1.6 times 10 to the power of negative 19 joule. So it's actually being described as the energy gained by an electron after it is accelerated through a potential difference of 1 volt. So let's say if you attach 2 points with 1 volt of battery, so here become positive point and here becomes your negative point. So based on Coulomb's law, we know that the electron here will be attracted to the positive terminal, right? Okay, so if you apply a potential difference of 1 volt here with a battery, so the energy that needed by this electron to accelerate from here to here, that is, this energy is equals to 1 electron volts. Alright, so you just have to treat it as a unit conversion only. Okay, so if the question gives you the energy in terms of electron volts, just convert it into joule. Okay, because again, joule is the SI unit of energy. Okay, so let's move back to the work example of our parallel plates, electric field in between 2 parallel plates. Okay, this question. Work example 3. A separation of 4 centimeter given an electron with 25 kilo electron volts of energy. Yeah? So what is the electric field strength between the 2 plates? So to find electric field for 2 plates is given by potential over distance. So we have the value of D, but we do not have the value of volts. Okay, so the voltage is given by energy divided by point charge. So the potential energy is 25 kilo electron volts. Convert to SI unit, which is in joule. So 1 electron volts equals to 1.6 times 10 to the power of negative 19 joule. Divide by charge. So 1 electron. Yeah? So charge of electron is also a constant 1.6 times 10 to the power of negative 19. So the voltage is 25 kilovolts. So to find your electric field, kilo times 10 to the power of 3 divide by the distance 4 centimeter, and the electric field is 625 kilovolts per meter. Okay, or if you want to put nano per coulomb, also the same, but this one volts per meter also acceptable. What force would this field exert on a piece of plastic with 0.5 microcoulomb? So in order to find electric force with a non-electric field, we can just straight away use the shortcut method. The charge 0.5 micro is times 10 to the power of negative 6. Electric field 625 kilo, and the force needed is 0.31 Newton. Okay. So let's recall what we have learned today. Coulomb's law, the formula related, okay, Q1 Q2 over R squared, and it is a vector quantity whereby if you have same charges, then the force is a repulsion force. If it is opposite charges, then it will be attractive force. Electric field given by KQ over R squared only. So it is also a vector quantity. If it is positive charge, then the electric field will be radially outward. Negative charge, radially inward. How to relate electric force and electric field? Force is related with electric field. Why? This. What is the electric field? in conductor. So electric field inside a conductor is equals to 0. But if it is around the conductor, then this equals to Q over R squared. Determine the electric field between two parallel plates is equals to volts per distance, and it's uniform in the whole area. Potential energy given by Q1, Q2 over R. So this is a scalar quantity. Potential KQ over R only, and is also a scalar quantity. Find the work done. So work done equals to Q times potential difference. So potential difference will be final potential minus your initial potential. Electron volts, so 1 electron volts equals to 1.6 times 10 to the power of negative 19 joule. Right, so this is the summary table of the whole topic. So what will be the application? Why do you need to learn until so complicated? Okay, the best application of electrostatic is the touch screen that we always utilizing nowadays. Okay, so it's based on the charge on our finger. So that's how they detect, or how they actually, how we say, the touchscreen is so efficient. In old days, the touchscreen is being detected based on human's body temperature, or the human the texture of the body. However, now it is based on electrostatics effect, okay, due to the difference in charge. So this one, it will cause the touch screen surface become more efficient rather than old times. Okay, so that will be the application. But in fact, in the process, from what we have learned today, until someone go and develop this one, there is a very long journey, but they are all starting from the fundamental. And another one will be the plasma ball. All right, so this is also another application, but I see it as a good way for us to illustrate all the equipotential lines and also the electric field. Right, so that's all for today's. Oh yeah, one more, the weekly challenge question. So this is a 1-star question. Yes, there will still be tutorial workshop, okay, but it will be a recorded one. If you cannot join, then please watch the recorded video, okay, after tomorrow. Okay, so since this is something which is very fundamental, so the question is also quite simple, but I just want you to grab the concept of what is the 4 terms that you have learned just now. Remember, electric force, electric field, potential, and energy. Force and field are vector, potential and energy are scalar. Okay, so I will post this on the forum later. All right, so if no more question, then I won't take much of your time, so you can go now to do your revision for maths. Tomorrow there will still be tutorial workshop, but if you cannot join, remember to watch the video. Right, So all the best and see you tomorrow or next week. Example 4. You mean the work example, huh?
Miss.
Yes. Is it this one? Yeah. Okay, all the best, yeah.